So the differences between work, energy, and power are critical to our understanding of a lot of mechanical and electrical engineering systems. So we're going to review that here. So in terms of units, let's take a look at work. So work is traditionally one of the most popular ways we talk about work is we say force that does something, right? Or force over a distance. And this is sort of a slang way of saying that. We don't mean over as in divided by distance, but a very popular formula for work is work equals force times displacement d, where the units for that would then be newtons for the force times the meters, the distance that it went. So let's remember what a newton is. The base units, the base SI units for Newton are kilogram, of course, kilogram meter per second squared. So therefore, the units for work would then be our newtons per meter, right? So we're just doing units here, would be newtons times meters, and that would be a kilogram meter per second squared times a distance of a meter, giving us kilogram meter squared per second squared. And a kilogram meter squared per second squared, we might recognize this, and this is the unit for a joule. And where a joule is a measure. The joule is the base SI, or not the base SI unit, but it is an SI unit that is a measure of energy. So we have mechanical energy in joules. We have, all of the mechanical energies like potential energy, kinetic energy. We have our thermal energies that are also measured in joule. We have our electrical energies are measured in joules, etc. So energy is measured in joules, and the base SI units for those are kilogram meters squared per second squared. And if we look at this kilogram meter squared per second squared, that's the same as we got here. So we can conclude that work, even though we know it's a force over a distance, or at least it's a force that does something, it makes it move, it makes it rotate, and something happens, we can also say the work must be energy. It's a word used for energy. And when we're talking about energy, energy is not a rate. Energy is not a rate of change. Energy is a quantity. Energy is something that like you could fill a bucket with. So energy, you could actually put in a bucket. Okay, of course you can't put it in a bucket, but you can have more energy, you can have less energy. There's not a rate of, it's not anything to do with a rate of change of anything. You can make more of it, store more of it, use more of it. Energy is quantity. So you can add up how much you used this part of the month, 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 this part of the month. For example, of electrical energy, it is a quantity. It can be created or just it cannot be created or destroyed, but it changes form, right? But it's a quantity, and I like to say bucket of energy. So I paid for, or I made, or I put an expense in for this bucket of energy. Is it a lot? Is it a little bit? It is a quantifiable amount. It is an amount. And that's different than a rate. So talking about amounts are different than talking about rates. If we talk about a rate means divided by time. It means something is happening over time. So if I go a rate, equals something over time. And if that something is energy over a certain amount of time, then that is power. That's the definition of power is energy gained over time, energy lost over time, energy changed over time. But it is energy over time. But I also said that energy is the same as work. So it could be work over time. But at any rate, it is definitely Newton meters over time, or it can be expressed um, in joules over time. And time is the base SI unit for time is seconds. So we can say it's joules per second. So therefore, power is measured in joules per second. It is joules per second. But the base SI units for a joule is a kilogram meter squared per second squared. And we're going to divide that by another second, which gives us kilogram meter squared per second cubed. This is a base SI unit. Base SI unit of power. So power is the rate of work being done or work being consumed. It's the amount that I had to fill this bucket with over a course of time. So if time, now we'll change colors here to look at this concept. If time, if it took a really long time to fill that bucket, then long time to fill the bucket, then the denominator is larger and then the numerator or power is going to be small. Small power. If we filled this bucket really, really short, so we are quick to use the power, then that is very high power. If we need to use a bunch of power really quickly, that's a high power application. If we make a bunch of power really, really quickly, then that's a high amount of power that is a high power application. It's not a high amount of power. It is a high amount of energy in a very short time, which is a rate which we would call high power. And one more thing I want to talk about the difference between work, energy, and power. Often misunderstood perception here is if I ask, what is a kilowatt hour? A kilowatt hour we often see on such things as our electricity bill. So we say that we used this many kilowatt hour of electrical energy. Used X amount of kilowatt hour this month. And you have to pay for that. Is that power or is that a quantity? Well, if you use that amount this month, you're not talking about a power because it doesn't say you used, it doesn't say you were really quick this month. You were really slow this month. It's not referring to a rate. It's referring to a quantity that you used. It's referring to a bucket and you used this much in it. You used this much. So I would hope that if I'm going to use a quantity, this is a quantity, I would hope that if I'm going to use a quantity this month, then the kilowatt hours is actually a measure of a quantity. Or sorry, of energy, not power. So let's take a look at that. So we know what a watt is. Did I say what a watt was here? Oh, sorry, I should have gone back here and said a joule per second classically is what a watt is. It's a joule per second. So in this application, I'm gonna just look at the types of base SI units here that I have here. I have kilowatts. I'm going to get rid of the kilo for a second here, and I'm going to say watts. So basically it's a watt, but a watt is a joule per second. and it's times time. So really this is a watt, or it's a kilowatt. We can just move some decimal places over time. But a watt is a joule per second times the SI unit for second is time. And if we break down a joule into its base SI units, then we remember that a joule is a kilogram meter squared per second squared. We kind of have that on the top of our head, and we've also said it here and up here. So this is a kilogram meter squared per second squared. That's a joule divided by seconds, and that comes from, well, I'll explain it in a second. So that's divided by seconds times seconds. So let's highlight this to make sure that we know where it came from. Here's the divided by second. Here's divided by second. And here's the joule. And a joule is a kilogram meter squared per second squared. And here is the second, because we said it's watt times time, and time has a base unit of seconds. So then it's a simple matter to go through. Cross out seconds because this is on the numerator, this is on the denominator. I'm left with a kilogram meter squared per second squared. I know that a kilogram meter squared per second squared is a joule. So what we have done here with kilowatt hours is we've said rate times time, but we know that this rate is energy over time. So we've said energy over time, and we have multiplied that by time. We cross out those two times and it's energy. Therefore, a kilowatt times hour is a measure of energy, not power. It's a measure of energy.